All right, so next up, we have Greg Chesterton, who is a colleague at IDA. Greg is a research staff member here who has a master's degree in operations research from the Naval Postgraduate School, as well as a degree in aerospace engineering. Greg served time in the Marine Corps as a naval flight officer. And has also spent time in the trenches of Makatia, the Marine Corps Operational Test and Evaluation body. And after retiring from the Marine Corps, Greg has also spent some time at MITRE evaluating safety risk for FAA sponsors, and now is here as part of our live fire portfolio. His interests are in design of experiments, data analysis, and statistical inference, and he will be talking about how to quantify unobserved and difficult to count problems in populations.
So I've been here about a year, and I've been working on the fixed wing task with Jim Rhodes and live fire, as was mentioned. And about halfway into my tenure here, Jim was showing me some data from OEF and OIF, some aircraft combat loss data. And it's a very detailed database that has a lot of information about causal factors associated with each of these combat losses. So it's a really interesting data set. But at some point, I asked Jim, is this a comprehensive data set, or are we missing any? Do we know about all the events that happen? And he said, oh, no, certainly we don't. There's a bunch of missing events that we don't know about, and we have no idea how many of those that we don't know about. I said, I think I know some techniques we can throw at this problem to try and answer that question. Sometimes we really want to know what the denominator is. If we're trying to quantify some other percentages, it's useful to know how many we think are in the total population of a certain kind of event of information. So if you recall back to the late 90s when we were working with the Kosovo situation, there was reported occurrences of ethnic cleansing and that sort of thing. And there were some international rights groups that had gone around and collected data on deaths and went house to house interviewing people. And they came up with a number of about 4,400 unique IDs or unique, I won't say social securities, but personnel IDs. So that was the total number of unique individuals they knew about across these four agencies' data sets. And some statisticians took these data sets and applied some of the techniques I'm going to talk about today to come up with a revised estimate of how many they thought really happened based on those 4,400. And their number was quite a bit larger than that. And I'll get back to that in a bit. So much like Justin did in his approach and with his techniques, before I tested some of these techniques, I wanted to get comfortable that they were accurate, that they were that I could apply them using the tools at my disposal. And I wanted to know how accurate they were against a known data set. So I created a synthetic data set, much like that looks like we would come across in natural occurrence. So in this case, I've got some population of events out there, and I've got three different groups of people that are going to go out and collect these information about these events occurring. And you can tell from their results there that they have different degrees of success. Group A there finds much larger than the other one. So each of these groups has some probability of discovering the various events that are underlying there. And since they're each producing different numbers of events, what's a good estimate for the total population that they went out and were looking for? How many actually occurred out there? Do we just sum up the values, that they had here? If we do, they come up with 855. Is that a good estimate for the total number of in the population? Well, as you might imagine, there are some that would not account for double counting if there's events that occurred across the lists. So that's probably not a great estimate. If they took the trouble to eliminate any duplicates and they only had, let's say, 600 unique events, 688 in this case, is that a good estimate? That might be undercounting if there's, occurrences that are out there that none of these groups saw. And you have reason to believe that there are other events that none of them saw because there's events that are appearing on some lists and not others. So really, we need a formal method where we can come up with a better estimate for what we missed out there. So if you think of it visually, you've got this, you've got an overall population of events, you've got some subset of those population of events that appear on list A and list and B. Some of these events are going to appear on 2 or more of these subsets, like you can imagine here. And then you've got some events that are outside of anybody's list, but they're out there in the population. And of course, those are the ones we really care about. That's the troubling number that we're really trying to get after. So before I go into the specific synthetic data that I ginned up, I just wanted to kind of hit on your basic intuition of this problem. Imagine you've got a population of events out there and you sent 2 groups out there to do their thing to collect information about these events, and they report back. They're working independently, and these 2 groups come back and you look at their lists and you look at the ID numbers on their lists. That's all those numbers are, is like unique IDs. And you notice that both groups have come up with the same exact events. Well, in that scenario, you'd kind of think, well, if they're finding the same events, there's probably not a whole lot out there that aren't discovered. There might be a few more than 5, but you don't have reason to believe that there's a ton more out there, or else they would have had some different events on their lists. And if you contrast that with the other scenario where they come back and there's nothing common between their 2 lists, in that scenario, you would think, geez, there's probably a whole lot of events out there or people or whatever they're counting that neither group knows about. Otherwise, they wouldn't have come back with completely unique lists like that. So intuitively, we learn that there's something about the overlap, the degree of overlap between these groups that is telling us how many are out there that we don't know about at all. So we're going to take advantage of that missingness, if you will, to tell us how many is out there. So a lot of these methods were invented by ecologists because they are interested in estimating wildlife populations, which is why a lot of the terminology from this area sounds a lot like capturing critters. You know, there's terms like capture and marking and recapture. I'm sure some other ones will pop into my vocabulary here that over the course of this. But essentially, there's other applications, obviously, but they're the ones who really fleshed out a lot of the science behind this and are dealing with a lot of the nuances of these techniques that make them trickier. So here's a very basic example. You might have learned this one back in grade school. Imagine you're trying to estimate, number of fish in some lake. They're out. It's a mystery how many are really out there. So you capture a bunch. Let's say you've got 10. You mark them all, you throw them back in the lake, you wait long enough for them to remix into the population, and you do another capture. And you notice in that recapture, capture number 2, that 5 of the 15 are marked from your previous marking of those fish. So that fraction, 5 over 15, should be the same as the number that ratio should be the same as 10 that you originally caught and marked out of the overall population. You just reorganize those numbers and you come up with an estimate of the population. And that's the Peterson estimator, which is the most simple, basic estimator of that population. Handy, but it sits on a bunch of really tight assumptions that are hard to reach in many of the applications that we're going to be dealing with. For one, you need a closed system. That's easy when you have a lake and fish aren't going anywhere in a short period of time. But in the kinds of things we're studying, it's a little trickier. We usually consider a closed population to be defined by a start and end point in time. So we make sure that the data that we're looking at are constrained by the same time window, and that prevents migration, if you will, in and out of the population. We also need homogeneity for this simple 2-case example. Homogeneity means that the probability of being captured, each individual has the same probability of capture. So you don't have, as ecologists call it, trap happy or trap shy critters. When it comes to people, you don't have subpopulations of people that don't want to be identified or do want to be identified. If you have that situation, you have to stratify your samples or block, like the term Justin used. And so we have techniques to get around that, but that's an issue. Independence. That's the requirement that the probability of you appearing on one list doesn't affect your probability of appearing on another. How could that happen? Well, critters learn that that's a trap, and so they don't want to be caught again, or they like the trap because there's food in it, so they do want to be caught again. With people, it means that the group A that's collecting stuff isn't cheating and looking at group B's efforts, and then you got lists that aren't independent anymore. And so if that happens, we have to deal with that mathematically. And then perfect matching. We have to know that if we're looking at an event or a person or something on list A, and it's also in list B, we need to be able to know that it's the same person or event, and keep track of that, because that's what makes this whole thing work, is the linking of events or people or whatever's animals across lists. The good news is that as we get more and more lists, instead of just 2 or 3 or 4 or 5, as that number of lists and sources goes up, we can relax a lot of these constraints, and they're not nearly as troublesome as the 2 list case example that I did. So deduplication and matching, I'll go over this real quick. Fortunately, in my case, for the data that Jim was working with on combat OEF data, he and his team had already done all this ugly work, because this is really the hard part. So deduplication is making sure that with any single list, you don't have duplicates, because of typos and that sort of thing. Not a super hard problem when you have a small number of items, and humans are usually pretty good, if they have the right context, at being able to tell whether 2 events are the same or not. It's a lot harder to get a computer to do that because a computer is going to detect any difference and think that they're different. So it gets a little trickier there. And if you do brute force pairwise comparisons, you can see how the combinations explode there. With 10,000 records, you'd have over 50 million pairwise comparisons. So it can be very intractable. We can make it more tractable by using techniques like blocking. I won't go into that here, but you can imagine if you stratify the problem, then you can reduce the number of pairwise comparisons that you have to do by orders of magnitude, which makes a huge difference if you're dealing with human interpretation of these records and deduplicating them. The other half of this is matching across lists. So in this little toy example here, we've got 5 individuals from the list on the left that are also in the list on the right. It's very tempting when you're counting events like this to remove the ones on the right and say, oh, we've already counted that. We don't want to do that. We want to leave them right where they are, but just make sure that we know that they're the same events and keep track of how they appear across multiple lists. Okay, so we're all familiar with Venn diagrams. They're very handy to depict it visually, but once we get computers involved, we need a more compact way to show how events are appearing across multiple lists. And so the inclusion history there, which is the far right-hand column, is kind of a shorthand way to show how an event or a person or a record appears across multiple lists. So the example there at the top of the list, event number or ID 451, you can see the inclusion history there on the right is 010. That says they're absent from group A, they're present in group B, absent from group C, and so on. 452 there, 110. History means that it's in A and B, but not C. So now you've got a nice compact way of accounting for every unique ID's appearance in one or more data sets. So this is getting to a nice structured method where we can get computers involved. We can take it a step further and aggregate across inclusion patterns. So if we go back to the example synthetic data that I had earlier, where we had 3 groups of data with 688 unique IDs, those can only fall into, when you have 3 groups of data, there's only 8 possible combos of patterns that they can fall into. And only 7 of those 8 are observable. The one there at the top that one, is pattern 000. That we don't know how many are in that group. That's the one we care about. That's the one we're really trying to estimate. We can't put a 0 there because 0 would be a known number. We don't know how many are in that top pattern of 000. But all 688 events from my synthetic data set are accounted with that little inclusion table right there. And we can feed that table into some techniques and get some answers. Quick sidebar here. I showed a Venn diagram of 3 cases. You know, when you have 3 overlapping data sets, a Venn is manageable. But above that, once you get into 4, 5, 6 or more, a Venn diagram is a pretty ugly way to show actual quantitative overlap between sets. So some of you may have come across this. It's called an upset plot, which is a nice handy way to show overlap more formally and I don't know. It's certainly more useful once you get up into above 4 sets. But even with only 3 here, it's more precise when you're trying to get a glance at the area or the height of each of these bars. So the bars on the left side, the left margin, are the actual size of each set, A, B, and C. And then the vertical bars are the size and the intersections. And the intersections are represented by the little dot patterns. So let's say the overlap between let's B and AB, is 109. That's the third vertical bar. The little intersection pattern there tells you what 2 or 3 overlap sections are accounted for in that bar. So again, all 688 unique events were accounted for in this plot. It's kind of handy. That's Upsetter in R will create these for you. Okay, so this is where the magic happens. Once we've got counts for each of those inclusion patterns, we're really teeing up for Poisson regression or log linear regression. So this is kind of where the magic happens. Each of those 8 different inclusion patterns is accounted for in the first column. Again, we don't know how many are in the first pattern 000. The second column there is the number of times that thing or event is observed. So with basically it's the sum of the number of ones that you have in each of the patterns. It was observed once, twice, or 3 times. The third column there is the probability that it's going to fall into any one of those patterns. And the fourth column is the expected count, which is just the population times that probability. And then lastly, we have the observed count. That's how many from my synthetic data were observed in each of those patterns. So with that, we're set up for a model, a log linear model, where our expected count, the log of that expected count, is a linear combination of the predictors, which in this case is our patterns that you see there in column 1. Those are our predictors. So that's our log linear model at the top there. And we can take advantage of this very convenient outcome that exponentiated gamma term is the exact value we need at the top of our table there. That expected count of that unobserved pattern 000 is simply the gamma parameter out of this model exponentiated. And so for our synthetic data, I did a best fit of that model. The gamma estimate was 6.187. We exponentiate that and we get 487. So that's our best estimate of the number in that first block there at the top of the table that are in the missing pattern. You add that back to the 688 we saw, and we're 1,175 is our best estimate of the population of this group. Since we started with 1,000 in my synthetic data, it's not too far off. It overestimated a little bit because I threw in some extra overlap between those groups that this model didn't account for. So I'm going to test some R packages and get comfortable with whether those are producing estimates that are at least in the ballpark. The first one I looked at was called R capture. It kind of does a brute force of every possible combination of model. It's starting with the fully saturated model with all the terms, and then it starts dropping terms and it rank orders them according to the criterion you choose, which in this case was the criterion on the far right. It's called the BIC, or the Bayesian Information Criterion. And so the one it likes is the one that's at the top there, the one that only has main effects terms. That's that first column there is kind of ugly shorthand for the different terms that it included or excluded from the model. And the abundance column there is its estimate, each model's estimate of the total population. And again, I know that the underlying population that it's working on here is 1,000. So some of these are pretty close, some are overestimates. But the frustrating thing here is that, you know, the Bayesian information criterion on the far right ranks these all pretty closely, and yet the population estimates differ by up to a couple hundred. So what do you do with this? You know, how do you choose which one's the best or average them together? Fortunately, there's an app for that. There are R packages that will take the output of R capture and do some Bayesian model averaging. I think the DGA is the title of this R application. I'm not seeing my notes here actually, so I'm just kind of winging this. So you can see the underlying, the dashed line populations are each of those models here. And then the bold line is sort of a Bayesian weighted averaging of those underlying models. And from that, that's a posterior. We can draw from that posterior and actually derive a credible interval, a 90% credible interval. In this case, ranges from about 900 to 1184. So now we've encompassed what we know is the true underlying population size. So we're getting some methods here that are encapsulating the true underlying value of our synthetic data. So that's pretty good. So I'm building confidence in each of these tools. The last one I did was called LCMCR. It uses latent class models and specifically a Bayesian application of those. So this is kind of the cutting edge of what's available in R packages to apply these methods. And when I applied it to our population and sampled from the posterior, I was able to produce a 90% credible interval from that posterior that ranged from 913 to 1300. So again, I've encapsulated the true underlying population there of 1,000. The mode of this population is, distribution is pretty close to our known value. So I'm pretty comfortable that our techniques are working well here. So now I'm ready to apply these to our combat loss data. Here's the upset plot that shows the distribution of all of the source data for the combat data. We had 7 different sources producing estimates of aircraft combat losses, labeled A through E there. And you can see the relative numbers of events that were recorded in each of those 7 sources. And then across the horizontal is the intersection of events as they fall into 1, 2, or more overlapping sets of those 7 data sources. So we had some, actually with seven different sources, there's 128 possible combinations of all those 7 different overlapping areas on a Venn. I've only shown the 27 where we actually had results. The other 100 or so combos had no observations in those intersections, so I just left them off the chart. You can see where the bulk of them are falling here and they overlap between sets B and E, but we had some that are out there in a 3-way intersection. We had several that are out there in 3-way intersections. I don't think we had any in 4 different sources. I think the most we had was 3. But this helps to visualize, hopefully a little better than an ugly Venn would have, where we've got intersectionality between events across data sources. And I didn't apply every one of the techniques I've already talked about to this data set. I jumped right to the LCMCR technique that I talked about. And here's what we came up with. Recall that in our combat data, I probably failed to mention this, but in the combat data, we had 2,190 unique events across those 7 data sources. Like if you looked at the unique IDs, there's 2,190 unique values. If we apply this technique, you're looking at the posterior distribution here, and we take a 90% credible interval, and it ranges from about 2,500 to 2,800. So the true value of the number of losses is probably around 2,700, not the 2,190 that we observed. So we have some formal way to estimate the number of events we probably didn't know about out there. So it's quite a few. Now, if we go back and revisited some of these sources and found out, oh, wait, some of these really were identified and there was more overlappedness in our data than we knew, then that would revise this estimate and it would shrink down towards the original number of observed counts. But where we stand right now, this is the best estimate we can produce. So that's kind of the three takeaways. I guess it's a technique that takes advantage of the absentness of data across data sets to come up with a better overall estimate. It really does require quite a bit on that grunt work of deduplicating and matching that I conveniently glossed over in the middle there. But the other takeaway is that these are readily available applications in R, and they're not hard to get interesting results out of after you get your data in that structured tabular format that I showed. Just to kind of come full circle and put a bow on this, that human rights group that was working on the Kosovo data, remember I said that they had taken in data from 4 different groups that had 4,400 unique IDs on it. This group came back with an estimate of about 10,500 as a revised total estimate back in 2001, just a few years after they were asked to look at the data. And that data was subsequently used in all of the criminal trials against Milosevic. And in the intervening years, in the decades since, they've actually done much more exhaustive, house-to-house estimates of the total number. And the total number is about 10,500. And their original estimate decades before only missed by a few. So it was pretty amazing how accurate their estimate was using these techniques. That's the HR DAG that's mentioned in some of the references there. What's really great about the work that they've done is they are very transparent about all the data sets that they've used. They're strong believers in reproducible research, so you can go back and reproduce all of these numbers. They share all of their databases. They share the R code that they've developed. They're behind a lot of the R packages that you can find in the repo. So with that, I'll turn it over to any questions. And if you think of some later, I'm happy to answer them offline.
How did you check how different your more complicated estimate was with the final regression model versus if you used the simple fish example that you showed us with your 2 large data sets?
That's a good question. I didn't. I didn't. No, I had read enough about how these more sophisticated techniques handle a lot of the biases that if you don't address them, you're going to get poor estimates. But that's a good idea. I should go back and say, well, all right, what if I didn't know about any of these? And I just
2
used
of them were quite a bit larger.
Yeah. Mm-hmm. That's a good example. Good point. I'll go back and do that.
What's the definition of combat loss?
Well, some of that gets into classified stuff, which is part of the frustrating thing. I can't share the nuts and bolts of the actual underlying data here at upcoming conferences that I would like to show this at. But
an event with 1 or more than 1 casualty, or you can't say.
I can't say that, but what I did ask when I was first exposed to this data is, do they all share the definition? That's important. Each of those 7 data sources needs to be producing something that they all have the same shared understanding of what a combat loss is, or else we'd be comparing apples to oranges. So in that respect, whatever definition they were using And I don't believe it did include strictly casualties. But they did share, according to Jen, they did share a common definition.
The effect of which combinations are observed between the lists, like if they're spread out over all of the combinations, does that give you a better estimate than if you only observe like two combinations of which lists they're on in your Venn diagram?
If you have the extreme case where you have no overlap between your groups, that's going to produce a bigger estimate. So if it really is the case that there's a large population of unobserved events out there, then you're on the right track that you want a bigger estimate. That means the absence across those lists is going to produce a bigger estimate. What you wouldn't want is you're missing them for some systemic reason. Like if you have some events out there that just don't want to be discovered, then they have a different probability of discovery, which is non-homogeneity, which there's special techniques for dealing and stratifying.
The Bayesian methods, you know, there's more uncertainty then, there's like less in common between the lists and you get a big number instead of a big number with a lot of uncertainty.
Oh, I would suspect so. Yeah, I would suspect that there would naturally in that posterior distribution be a greater variance with a greater number. But that's an interesting question. There are a lot in the literature that I showed there. Most of the academics start with a synthetic data set that has a very specific problem or bias injected into the synthetic data because they want to try some technique on teasing out whether it's good at uncovering that problem area. So yeah, I would encourage you to, anybody who's interested in this, to take a look at some of those references and any literature associated with MSE or multiple system estimation.